Okay, good morning, everyone. Today I want to cover the two examples for Thevenin and Norton circuits, which have been actually taking longer than expected for both sections. So almost start. Let's start about 10 seconds early. And let's bring up the class notebook. Section 4. And take your calculators out, and we will solve this as we go along. Okay. I mean, you will solve this as we go along. So first thing to do is to look at the problem statement. The problem statement is find the Thevenin and Norton equivalent circuits if the 2 ohm resistor represents the load resistance. What does that phrase mean? Represents the load. Load is the follow-on circuit. It also is the same as the phrase as seen by. Okay, the phrase as seen by. So you determine the Thevenin and Norton equivalent circuits as seen by the 2 ohm resistor. When you see or read these words, the phrase, that component is not part of your analysis anymore. The 2 ohm resistor should not be part of your analysis. Okay, that's the first thing. Now, it's also asking you to find all three quantities, Thevenin and Norton. So you need to find Thevenin resistance, Thevenin voltage, and the Norton current, right? All three of them. All three analyses are independent of each other, right? So you first find Thevenin resistance, then you find Thevenin voltage, then you find Norton current, or any order you choose, which is fine. Okay, let's start with Thevenin resistance. So draw out the circuit that you think is required to determine Thevenin resistance. To do that, you take a look at the circuit, you draw out all of the resistors as they are. You have to define your analysis terminals. In this case, 2 ohms is not part of the analysis. So when we remove the 2 ohm resistor, we are left with open terminals A and B. And A and B are the terminals of analysis. Terminals of analysis. Okay, 2 ohm resistor is not part of the analysis. You remove it and you label the terminals whatever you want. Here it is noted as A and B, so we'll stick with it. But if it's not, label it X and Y, 1 and 2, Batman and Robin, doesn't really matter. You're simply analyzing between those terminals. Okay, as I said, draw out the circuit for Thevenin resistance, or you draw out the circuit to determine Thevenin resistance. You might see that on the quiz. You will see it in the final exam. All of the phrases, it will be your job to recognize what the problem is asking of you. Draw out the resistors, not the 2 ohms. Reduce all the independent sources in the circuit to 0. The only independent source we have here is the voltage source. What happens to the voltage source? We replace it with a wire. So short circuit wire in place of the voltage source. If there was a current source, open circuit. Same concept that we use for superposition, right? Same concept. So your circuits should look like this. Thevenin resistance. You draw out the circuit as it is. 12 ohms, 4 ohms, 6 ohms, in a short circuit wire where my voltage source was connected. This is terminal A, this is terminal B. REQ, total equivalent resistance, is measured between those two terminals. What answers did you obtain for REQ? 7. Anyone? Anyone for 6? Anyone for 8? Anyone for 9? 8? Anyone 9? 8.5? 8.5? Anyone for 8.5? Anyone for 7? Anyone for 8? 8, 8, going once, going twice. Sold. REQ, if you look at the farthest end, we see that a 12 ohm resistor is now connected to the 6 ohm resistor. So we see 12 is in parallel with 6 plus 4. So by the way, to all students, I mean, I sometimes the material gets dry, I know, but I want to increase participation, right? So it's not a verbal quiz. If you speak up, you think if it's wrong or incorrect, doesn't really matter. Just speak up, right? That will be actually a learning moment. So 12 in parallel with 6 with 4 ohms. So that gives me 8. Okay, how about Thevenin voltage? Thevenin voltage. The circuit to determine Thevenin voltage is completely distinct, or it's completely separate from the one that we used to find Thevenin resistance. Remember, 3 quantities, 3 independent analyses, 3 completely different and distinct circuit diagrams. So the circuit that we used to find Thevenin resistance has no bearing whatsoever on the other 2 analyses, meaning Thevenin voltage, different circuit, Norton current, different circuit. So now draw out the circuit that you think would be required to analyze for Thevenin voltage. It's rather straightforward. You simply forget about Thevenin resistance, go back to the original circuit. You draw out the entire circuit as it is, except you keep the analysis terminals open. In this case, again, 2 ohms is not part of your analysis. When you remove 2 ohms, you have terminals A and B. You keep those terminals open. So we'll draw out the circuit as it is. A and B are open. I'm going to assume my polarity as plus at A and minus at B. You can choose the opposite if you wish, doesn't really matter. This is just standard convention. Voltage source has a plus up top, so current would be flowing up. Current flows up, makes its way from the left to right. Logically, I would think that A would be higher than B. So I choose A as plus, B as minus. Okay, what techniques come to mind? I'm to label this as C, label this as node D. You have 4 nodes, you have 1 mesh. What do you think? You can use any of the techniques. You can do node voltage analysis, mesh current analysis, series parallel analysis, we reduce down to one single circuit. But I specifically like this circuit configuration because it's a teaching moment about an important concept. It's a one-step, one equation answer. Let me ask you this. What is the relationship between the three resistors? Are any of them in series? Are any of them in parallel? Are any of them in parallel? No, because for parallel connections, you need two of the nodes to be connected to two of the other nodes respectively, right? So here we can see at node D, all three resistors are connected together, but they are not connected to any of the other ends. So other ends are connected to A, B, and C, completely different. How about series connection? Right? Series connection also doesn't make sense, but the answer is actually yes. And I'll tell you, the two resistors that are in series are 12 and 6. Now think on that and let me know. Does it make sense? And why it makes sense? Anyone? Yes. That is the answer, yes. The concept is, if you have a component connected at the node, but if the other end of that component is not connected to anything, current cannot flow through it. It's a dead-end street. No traffic's going to go in that direction, right? Current needs a closed pathway to flow through. All of our power outlets, we say the outlet is live, but they're open. They are not connected to anything, not until we plug a device into a power outlet. So current is not flowing. There is voltage that is available, but current is not flowing through it. Otherwise, we'd see arcs coming out all the time, right? So current is not flowing through a power outlet, not unless and until we connect a device into the power outlet. Same concept. If one end of a component is not connected to anything, is just hanging in the air, no current can flow through that component. It may as well not be part of the circuit at all. If there is no current flowing through that 4 ohm resistor, what is the voltage across that resistor? 0 volts. They are both exactly the same potential. Voltage is the difference in electric potential between any 2 points. If the voltage across, if there's no current flowing through that resistor, voltage is 0. That means both of them are exactly the same potential. It means voltage at A is exactly the same as the voltage at D. This is the important concept I wanted to point out. And because that 4 ohm resistor is effectively not part of that connection, only the 12 and 6 are connected at that node, and hence 12 and 6 are in series. Does all of that make sense? Think on that. Let me know if you have any questions. In the meantime, I'm going to redraw the circuit so that it makes more sense visually. Any questions? Yes. So the question being asked is, if we use node voltage analysis, would we get the same thing? Absolutely, yes. You can use node voltage and you can use superposition. I'm sorry, not superposition, mesh current. Superposition wouldn't make sense because superposition is if you have more than one source, you break down the circuit, then you analyze it. So in this case, you can do series parallel analysis, you can do voltage division, you can do node voltage analysis, you can do mesh current analysis. All of them would give you the exact same answer. So I would like to always state to students, you can take the circuit, try to solve it using a different method. That would be good practice, especially since you already have the answer. Okay? Yes. So the question being asked is how many meshes do we see? It's basically how many closed loop pathways we have. There's only one closed pathway, so the answer is 1. Yeah. So one mesh current, one equation. We can just solve it with one equation. If you do node voltage analysis, again, it would simply be one equation because B is common. If you choose B as the reference, node B is VB is 0. VC would be 30 volts. D would be the only unknown in that case. You simply write one equation, you get your answer. But we need to find voltage, right? We are solving for Thevenin voltage. We want the answer for VAB, voltage at A measured with reference to B. In this case, VAB is the same as VD. This is D, this is A, this is B. If A is the same potential as D, that means I need to find the voltage across the 6 ohm resistor. And because 12 and 6 are in series, this is node C. Always advise students to redraw the circuit as many times as you need until it starts making sense. In a quiz, in the final exam, it won't take you more than 5 seconds to keep redrawing the circuit. Every redraw is going to take you 5 to 10 seconds. Keep track of the nodes, keep track of the components. And once you redraw it, it'll click. So in this case, since they are in series, I can apply voltage division. If I apply voltage division, I can write VDB is a fraction of 30 volts. The fraction would be given by the resistor to Req, which is 12 plus 6. 6 divided by 18, 1/3 of 30 gives me 10 volts. My VTH is equal to VOC, which is equal to VAB, which is equal to VDB, which is equal to 10 volts. Write it down, think over it. Let me know if you have any questions. Any questions? Does it make sense? Right. So simple circuit, again, you can solve it any method, but I like to use this as a teaching moment to show about, components that are not connected at one end. Yes. Sure. So the question being asked is when we redraw it, what is the best approach to redrawing, correct? So I would suggest or I would recommend you first note down all the nodes, mark all the nodes in the circuit. So as I said in here, in the original circuit, I noted down A, B, C, D, right? So 4 nodes. I make sure each node, or make sure of the components that are connected between each one of those nodes. So when I redraw the circuit, I can redraw it in a rush, that's fine. But then I just need to reflect back and think, okay, node A and B, is anything connected between A and B? Then I look back at my redrawing, A and B has nothing, no. Between A and D, I have 4 ohms. I need to make sure I have 4 ohms between A and D, and then so on and so forth. So you mark out the nodes, and then you look at each and every component that is connected between those nodes. When we first start out, it takes a while. So when I was a student, this is more than 30 years ago, when I first started out, I would keep redrawing the circuits. It would take a while, but then it clicks after enough time has gone by and you practice sufficiently, it clicks. It took me a while to get used to it. Some students get it much quicker. So my peer students, they got it much quicker than I did. But as I kept practicing more and more, one day I got adept at it, and a light bulb kind of like goes on, and then you get adept at recognizing circuits. So again, when you first start out, take it slow. Look at the nodes, look at the components that are connected at every single node. Make sure you're redrawing whatever circuit you redraw, make sure those components are connected between those nodes. That way you can be sure that your circuit is correct. Okay. All right. Any other questions? Yes. No. So the question being asked is, in the real world, if you did a measurement, like using a meter, would a node D or node A have different voltage? The answer is absolutely not. So the theoretical analysis, we make assumptions, but in this case, it's not we are not hypothesizing anything. This is a fact. So the answer would be that VD would absolutely be equal to VA. And again, students who are taking the lab, if you wish, you can try out this experiment. Once you get done with your measurements, just open one end of a resistor, recreate something like this in the lab, and just take a measurement at both ends of that resistor. And you'll be able to verify it yourself. Okay. All right, let's move on to the Norton current then. Norton current, if you draw out the circuit that is required to determine Norton current needs a pathway to flow through. So now at my analysis terminals, I have to connect a wire for the current to flow from A to B. Draw out the entire circuit exactly the way it was. I have the 12 ohm resistor, the 6 ohm resistor, and the 4 ohm resistor. So 12, 4, and 6. This is still, of course, 30 volts. This time, need a wire between A and B. I assume the current is going from A to B because Thevenin voltage, I assume the current, so the voltage polarity was plus at A minus at B. If you assume a polarity for Thevenin voltage, you stick with that same polarity. Okay, don't change it. You assume A is higher than B, so current is flowing from A to B. Don't change your analysis here. You can't change it by going from B to A. Norton current IN would be ISC. So what techniques come to mind? Mesh current analysis. There are two meshes. We can apply mesh current analysis, automatically get an answer for ISC. That's an obvious one. There's also, you can do node voltage again. Mesh current requires two meshes, two unknown variables, two equations. You do node voltage analysis, same thing. Now you have three nodes. A and B are now exactly the same node. Remember, if you have two nodes, they get connected by a wire, they become exactly the same node. So from 4 nodes, you're now down to 3. If this is C and this is D, A and B are the same node. You choose B as your reference. VB is 0. VC is 30 volts. VD is the only unknown left. Yes. Absolutely. Current division. We can find the total current that is flowing because of the voltage source. Current gets divided. You can apply current division. And you can find it that way. Series parallel analysis technique. All of the approaches are correct. Okay. No single one is correct or incorrect. As I said, practice using all different methods. That would just help in preparing. Okay, so let's do this. Because we chose with the series connection for the first one, I will do the same here. Redraw the circuit like this. And again, keeping track of the nodes. This is my 4 ohm resistor. This is a 6 ohm resistor. This is node D, where all of them are connected together. Power supply. So this is node C. And then power supply is connected at the other end at node B. One end of 4 ohms is A. A and B are the exact same. Whenever you redraw the circuit for Thevenin voltage or for the Norton current, VOC and ISC, always look for the component that is associated with these quantities. So VOC was associated with a 6 ohm resistor, right? We analyzed it. VOC is VAB, VAB is VDB, which is across the 6 ohm resistor. What component is ISC connected with or associated with? So if you take ISC, I will extend it in both directions. If I extend it here at the arrowhead, it doesn't really help me. Extend it from the tail end, and the answer absolutely is that it is associated with the 4 ohm resistor. Somebody did say 4 ohm resistor, right? So you extend that arrow in both directions and see which component it is associated with. In this case, ISC is the current that is flowing through the 4 ohm resistor. So we need to find the current flowing through the 4 ohm resistor. And as somebody pointed out earlier, we can apply current division to do that. But what I'm going to do is, since I used the same technique for the previous two sections, I will stick with that one here. I can find Vx by applying voltage division. 4 and 6 are in parallel. So 4 in parallel with 6. Two resistors in parallel, product of the two divided by the sum of the two. So 24 divided by 10 gives me 2.4 ohms. You apply voltage division and you obtain Vx is a fraction of 30 volts times 2.4 volts divided by Req, which is 14.4. This gives you a value of 5 volts. And this would be ISC coming from the 4 ohm resistor. 4 and 6 are in parallel, so the voltage across both of them is a result of the Req of 4 and 6. 4 and 6 in parallel is 2.4. That 2.4 ohms is in series with a 12 ohm resistor. You either find the total Req, which is 14.4, find the total current IT flowing through the circuit, then apply current division, or you apply voltage division first, find Vx, and then apply Ohm's law. Two different approaches, you should get the same answer. Does that make sense? I'll wait for you all to, if you're noting it down. Let me know if you have any questions. Any questions? Okay. In is 1.25 times 8 gives me 10 volts. The answer is verified. The final two circuits, final Thevenin circuit should look like this. Final Thevenin circuit. It's always the same. It's a voltage source in series with a resistor. That resistor is RTH, in this case 8 ohms. Voltage source VTH, which was 10 volts. And you plug that resistor back into the circuit, 2 ohms. This is how it should look. Thevenin equivalent circuit is always a voltage source in series with a resistor. That is the whole point of the analysis. So the final circuit does not change. The final circuit will always remain the same. Final Norton circuit is also the same. It's a current source in parallel with that same resistance. So it's IN. And you plug it back, that same circuit, 2 ohms. This is still RTH, which is 8 ohms, and IN, which is 1.25 amps. Does the procedure make sense? Does the method make sense? This is what I would expect students to do in the quiz and final exam. Okay, step-by-step approach. Yes. That is the equivalent circuit. Current source will always have a resistor in parallel, and a voltage source will always have a resistor in series. Because a current source will supply its rated current no matter what is connected to it. So if you're connecting a resistor in series with a current source, you cannot actually depict the real life resistance. I mean, real life current source. If you connect a resistor in parallel with a voltage source, what is the voltage across that resistor? It remains the same because it is in parallel. So if you need to show that some of the voltage is being consumed internally by the circuit, for a voltage source, you always state it in series. For a current source, you always state it's in parallel. Yes. Okay, so the question being asked is if there is no load given to us, meaning the 2 ohm resistor was not part of the circuit in the first place, then yes, you would simply leave it open. Then the question would simply state, determine the Thevenin and Norton circuits between terminals A and B. If the question states that for this circuit, if it simply states, find the Thevenin and Norton between terminals A and B, then you would not remove the 2 ohm resistor. Let me be clear about that. If the question states, determine the Thevenin and Norton equivalent circuits between terminals A and B, then you would simply analyze between A and B. You would not remove any component from your analysis. Is that clear to everyone? Right? We remove the component 2 ohms because of the phrase load resistance, which is also the case for the next circuit, which I need to pick up the pace. I'm going to have to rush this a little bit. Same circuit or similar circuit. Now, in addition to that, the 3 resistors, we have a current source also present in the circuit. Thevenin resistance is rather straightforward. Again, as I said, it's the same circuit for Thevenin resistance. I draw out the resistors and I reduce all independent sources to 0. Meaning the voltage source is replaced with a short. 5 10 and 20, A and B, REQ. Again, my notes and annotations are there in the class notebook. They are available to everyone. So it might be better if you, instead of writing this down, you might just want to pay attention to what I'm saying. So REQ in this case would be the same as the previous one, phi in parallel with 20 plus 10. That gives me a value of, let's see, what do I have? My notes, 14 ohms. Okay, 14 ohms. Thevenin voltage. You draw the original circuit exactly the way it was with all the sources back in the circuit. Terminals A and B, plus and minus, and then an additional current source of 1.5 amps. This was node C. This was node D. We'll stick with the same convention. And this is 20 ohms, and this is 20 volts. If I count the number of nodes, I have 4 A, B, C, D. Terminals should be open because the problem statement is still the same. It says, determine the Thevenin and Norton circuits as seen by the 17 ohm resistor. The 17 ohm resistor is not part of my analysis. My analysis terminals are still A and B. I choose A as plus and B as minus. A, B, C, D, if I choose B as my reference, VB is 0, VC is 20 volts. I have two unknowns, A and D. I can use node voltage analysis. So NVA, two unknown nodes, MCA, two meshes. So let's do NVA, node voltage analysis. B is chosen as my reference. Therefore, VB is 0 volts. And therefore, VC is 20 volts for the purposes of my analysis. That leaves me with two unknowns, A and D. In this case, A and D are not exactly the same because you have a current source in parallel with that 10 ohm resistor. Okay. So node voltage analysis requires me to assign branch currents. I'm going to assume a branch current for the supply, which goes up. It also goes to the 5 ohm resistor, splits between the two. This comes here. So the branch, these are not mesh currents. These are branch currents. Keep that in mind. These are currents flowing through each electrical branch, each electrical component. Okay, we call this I1, I2, and this is labeled as I3. These are the currents that are flowing through each one of those resistors. So if I apply KCL at node A, what do I have? At node A, I have the 1.5 amp current source coming in, 1.5 coming in, and I have I3 leaving. Automatically, I have a value for the resistor current for the 10 ohm resistor. I3 is 1.5 amps. If I apply KCL at D, I have four currents. I have I1 coming in. I have I3 coming in. I have the 1.5 amp leaving and I2 leaving. I3 is the same as 1.5 amps. So that cancels out, leaves me with I1 equals I2. Apply Ohm's law and express each branch current in terms of the node voltages. So I1 is equal to the difference between C and D divided by 5. Because I chose my direction of the current as coming from left to right, tail end would be higher, right? Current flows from plus to minus. So VC is higher than VD. So it'll become I1 is VC minus VD divided by 5 ohms. I2 is flowing from D to B. So it's VD minus VB divided by, what is it, 20 ohms? 20. I reduce this equation, and I would get, what do I get? Multiply everything by 20, I get 4VC minus 4VD equals VD. VB is 0, VC is 20. So I would get 5VD is equal to 80. VD is equal to 16 volts. The job is not yet done. I need to find the voltage at A, not at D. But I can use VD in any one of the equations. The equation that makes the most sense is I3. So for VA, I will choose I3. I3 is flowing from A to D, from right to left. That means A is higher. So VA minus VD divided by 10. Rearrange the terms, and you obtain VA is, actually, let's 1.5 is equal to VA minus VD, which is 16 divided by 10. So VA is 1.5 times 10, 15 plus 16 gives me 31 volts. Therefore, my Thevenin voltage VTH, which is equal to the open circuit voltage VOC, which is equal to VA, is 31 volts. That was the node voltage analysis method. In the years past, I've solved this using superposition. Superposition requires me to split up for both sources. One analysis for the voltage source, one analysis for the current source. You can try it. When you try that, for the voltage source, you would obtain 15 volts. Sorry, voltage source, you would obtain 16 volts, which is what you obtained for VD. And for the current source, you would obtain 15 volts. 16 plus 15 gives you 31. I'm going a bit fast, so let's take a pause before I move on to the Norton current. All right, any questions? Okay. Let's follow along to mesh current analysis for Norton current. So for Norton current, I'm going to choose mesh current analysis, but again, you can choose node voltage also. Let me first draw out the circuit diagram. Should have drawn it a bit larger. Current needs a pathway to flow through, so I'm going to place a short between the two terminals, A and B. Thus, A and B are exactly the same. In this case, this is a very unique, not unique case, but this circuit, it turns out that you have 4 nodes, but A and B are now connected together. So they're the exact same node. If they are the exact same node, and I choose NVA as my method, then I am left with only one unknown variable. If I choose VB as reference, VB is 0 volts, VC is 20 volts. The only unknown is VD, because A and B are exactly the same. So you have one equation to do. That's it. You find the node voltage, then you find the current. But I will choose MCA because I chose that for the other classes also. MCA, you have two unknowns. And I'll explain how. So I'm going to label this as mesh 1, label this as mesh 2, label this as mesh 3. For mesh 1, I choose a clockwise current. Mesh 2, I'll choose a clockwise current. Mesh 3 also the same. Now these are not branch currents, these are mesh currents. All right, I1, I2, and I3. Got 5 minutes left, so I'm going to write this out quickly. From mesh 3, I can write I3 is equal to 1.5 amps. Same thing again. And also I can write ISC, short circuit current, is I2. If I apply KVL in mesh 1, I have three quantities. Again, minus 20 plus 5 times I1 plus 20 times I1 minus I2. We are in mesh 1, all currents are clockwise, so I1 is positive, all other currents outside of I1 are negative. So I1 minus I2, you reduce this, you get 25 times I1 minus 20 times I2 is equal to 20. Equation 5 I1 minus 4 I2 equals 4. I'm going to label this as equation 1. Apply KVL in mesh 2. I only have two components. 20 times I2 minus I1. Now I'm in mesh 2, so I2 is positive. The other currents outside of mesh 2 are negative. So 20 times I2 minus 20 times I1 plus 10 times I2 minus 10 times I3 is equal to 0. Reduce this, I get 20 times I1. 3 times I2 is equal to 15. You can solve this with any method you choose. I'm going to call this equation 2. You can solve this manually. Equation 1 multiplied by 4 gives me 20 times I1 minus 16 times I2 is equal to 16. Call this equation 3. Equation 2 plus equation 3 gives me 20 I1 is gone. I'm left with only 14 times I2 is equal to 31. Therefore, I2 is 2.2142 amps. My Norton current, IN, is the short circuit current, ISC, which is the mesh current, I2, which is 2.142 amps. Verify your answer. VTH should equal the product of IN times RTH. So IN is 2.2142 times, what do I have for Norton? 14 ohms. Gives me 30.99 volts, which is approximately equal to 31. Sorry to rush through the end, but we have 2 minutes left. So if you have questions, you can think over this. Let me know if something doesn't make sense. The final circuits remain the same. They don't change. The values will change, but the circuits do not change. Okay. Homework for Thevenin and Norton. I'll post some hints sometime after reaching my office today. Look for it in the class notebook, also in the announcements. Okay. I will see you all on Friday. I'll be in my office if you have any questions.